Today we have Paramveer Dhillon. He is a postdoctorate fellow at MIT Sloan School of Management, and today he's going to be here presenting on linear methods for big data. Thank you.
Thanks, Pamela, for the introduction. It's a real honor to be presenting here at IQSS. Thanks for the invitation. So these days, there's lots of talk about machine learning and nonlinear methods, right? Sorry, I mean like deep learning and nonlinear methods. So this talk goes against the flow and talks about simple linear methods for handling with big data sets. So we're living in the midst of a great data and measurement revolution, right? Large swathes of data is being collected every second as we speak, and it tracks all our activities online. So not only is this data highly unstructured, but it also comes in different modalities. So for example, your online behavior on desktop, as well as on a tablet, as well as on a smartphone is being tracked every second, right? So as social scientists, it becomes for us to ask an important question, like how do you build statistical methods uh, that are fast and efficient to make sense of this data? And as social scientists, we are also interested in turning these models into actionable insights for us, right? So big data methodologies, they typically rely on ideas from computer science, statistics, and applied math, right? So, and there's a culture divide here. So computer scientists, what do they care about? Computer scientists care about algorithms that run fast, right? That parse through large swathes of data and come up with algorithms that are extremely fast to run, right? In particular, they care about this notion of computational complexity or computational efficiency, which is the big O notation, right? How fast is the algorithm as an input, as a function of the input data sizes? And they want the computational complexity to be lower and the efficiency to be higher, right? On the other hand, the statisticians, they care about building algorithms with strong theoretical guarantees. Statisticians care about concepts like consistency of an estimator, minimum variance unbiased estimator, best linear unbiased estimator, asymptotic normality, and bunch of other similar constructs, right? So ideally what we would want is, or the question that we would want to ask is, can we get best of both the worlds? Can we come up with algorithms that are both statistically and computationally efficient? That is, they run fast on large amounts of data, as well as you can prove strong theoretical guarantees about them. So in this talk, I'm going to propose algorithms that are both theoretically sound and fast for two popular statistical methods. So one of which is ordinary least squares, which I'm sure everyone is familiar with. The second one is canonical correlation analysis, which is also related to OLS, as I will show. In particular, I would show how to make simple ordinary least squares regression run fast on large amounts of data while preserving its statistical guarantees. And for CCA, I would show how to make it run faster, as well as how you can use it to generate word embeddings, which are useful for several NLP tasks. And as I'm sure some of you are interested in, like sentiment analysis of political speeches or topic analysis of congressional proceedings and so on. And as I just mentioned, I would show its application on NLP, but I've also done some work on using this for parcellating brain images, some neuroimaging work, right? So just to get our bearings right, so the model that I assume is a simple linear model with an additive error term, right? So the errors are homoscedastic with mean zero and variance sigma squared, and the purpose of statistical inference is to estimate this beta parameter. So the beta is the unknown parameter, p-dimensional parameter vector that generated the data. And the whole goal of statistical inference is to come up with an estimate for this beta, right? To come up with the beta head. And I'm assuming that you're given x. X is a matrix of covariates. It has n observations and p covariates, right? P features. And y is the vector of outcomes. If you have n observations, so it's n by 1. And the OLS solution, as we know from our Stat 101 course, it's like this, a simple estimate. It's x transpose x inverse, x transpose y, right? And in particular, I consider the big data setting in which n is much, much larger than p. Say n is like 10 million, and p is, say, is in a few hundreds. So now I talked about this notion of computational and statistical efficiency. So let's see what are the guarantees for this simple ordinary least squares that we are all in love with, right? In terms of the running time, its running time is order of np squared, right? So basically, what I'm saying is the running time is the run time of computing this x transpose x inverse x transpose y in the closed form, right? And np squared is just since I'm in the n much greater than p, so np squared is just the cost of this matrix multiplication. So note that in linear algebra, like inverses are also a very nasty operation to compute, right? Because and they are cubic in the size of the input. But since this matrix is p by p, so the inversion would be p cubed. It is absorbed here because we are in n much greater than p. So the cost, so the running time of this algorithm of this estimation procedure is order of np squared. For our purposes. And the error bound, which shows how the estimated beta hat deviates from the true beta that generated the data, it's order of square root of p over n. So as you can see, your notion of classical consistency that you hear about in statistical textbooks, it just follows from here. That as n approaches infinity, beta hat OLS approaches beta, the true beta, right? Yeah.
Question. So is this computational? Is this efficiency using any kind of decompositions that are typical in like statistical programs, like QR decomposition?
Yeah.
Okay.
Yeah. So it's just this. If you were to just compute this, like I'm not doing any QR decomposition or anything, but like this is the fastest you can get for simple OLS. I mean, you could also have done gradient descent, but for simple OLS, you can get a closed form solution. So why do a gradient descent, right? So, yeah. So now there's lots of work on fast least squares regression. I mean, lots of mathematicians and computer scientists have tried to tackle this problem. And all of these approaches have a similar template, which you might have thought of if I had just told you how would you make linear regression run fast, right? So what's the most intuitive thing to do? You subsample uniformly at random the X matrix, right? As I said, like n is much larger than p. So typically, if n is say 10 million, you would keep some n subs of those observations, say about 1,000 observations, estimate your regression on that, and we're good, right? So note that with this subsampling uniformly at random, there is a chance that you might miss some outliers or high leverage points. And as we know that the regression line estimate could be highly sensitive to those points, right? So in this literature, what it's typical to do is you precondition the X matrix, that is you left multiply it with a randomized Walsh-Hadamard transform. So think of it as like Fourier transform. So what it does is this multiplication, it spreads the signal uniformly across all the observations. Hence, you can subsample uniformly at random and not worry about leaving some outliers or high leverage points. So I will call this method fast subsampling, like either with the preconditioning or without the preconditioning with the Hadamard transform, it's the same complexity. So now let's see the guarantees for this algorithm. So basically what I have done is I have replaced n with n subs, right? N was 10 million, n subs is about 1,000. So the runtime is really fast now. So now you can see it's n subs p squared, right? However, the error bound is also equally bad because the n subs comes in the denominator, right? So here is the standard OLS that we like. It's you get the right error bound that you would want for a consistent estimator, but it's slow to run, especially for large data sets. And fast subsampling, it's really fast to run, but the error bound is not that good. So now the question worth asking is, can we come up with best of both the worlds? Can we come up with an algorithm that is fast to run as well as it has the required error bound? So I'm going to talk about this algorithm, which I call Uluru. Why it's called Uluru, I will explain in a minute. So it's both fast and accurate. So its runtime is order of np, and its error bound is square root of p over n as you would want. So note that if you have a data set of n rows and p columns, and it's lying on your hard disk, right? Even if you have to load that data into RAM, NP size data into RAM, it would take order of NP time. So this algorithm is fastest in the class of algorithms which look at entire data without throwing away some of the data without even looking at it. So this fast subsampling, which I showed, which is like I would say the industry standard, what it does is it would throw away lots of the data without even looking at it and would estimate a regression line, which could be biased in several cases, right? So now let's see what the algorithm is. So the algorithm is that first you get an initial estimate of beta hat using the fast subsampling algorithm, right? Let's call it beta hat fs. And of course, it would be biased. So the remainder of the algorithm, what it does is it would correct the bias in a way so that you get the correct error bound, but it also doesn't blow up the runtime. Like that's the main intuition behind the algorithm. So now, by definition, like if you were to compute residuals on the remainder data, like it would be like y minus x beta hat, right? So rem is so let's say if n was 10 million and n subs was 1,000, so rem is 10 million minus 10,000. So it's like the remaining observations, right? So you can compute residuals on the remainder of the data. And by definition of like a simple linear regression, if you were to just estimate a linear regression again on the remainder of the data, it's just the simple additive linear model that we saw earlier. And if you just substitute it back in 3, you get this equation, right? So as of now, like we have a beta hat fs, and we have another equation which deals with the remaining of the data which we haven't looked at. So now, so what we're going to do is we're going to estimate the big hat of this, beta minus beta hat, capital hat, right? That would be the most natural thing to do. So we estimate this beta minus beta hat using a second regression and just add it to beta hat fs, and you get the estimate, you get the required error bound, and it's fast. So now now some of you might be thinking it looks like a sleight of hand, like there is something definitely phishing going on here, right? So now let's look at this particular term, like how do we estimate this second regression closely, like to tease out what's happening here. So here's how we would estimate this, right? So you can see the speed bottleneck still remains. So although as I said that you could do this two-step thing, that is get an initial estimate and then correct it, but still, earlier you were estimating this quadratic term on 10 million observations. Now you are estimating it on 10 million minus 1,000, which is in the limit is pretty much the same. So we haven't gained much, right? So what the Uluru algorithm that we call it, why is it called Uluru? I would speak in a minute. So what it does is it says that you can replace this quadratic term by this. So instead of computing this quadratic term on 10 million minus 1,000 observations, you can just compute this quadratic term on 1,000 observations and we are good to go. So now, what are the conditions under which you can do that, right? So it turns out that if your estimate of the quadratic term is as solid as the rock formation Uluru, which is kind of a quadratic shaped rock in Australia, right? Then you would get the required error bound. And if you were to fix the amount of subsampling to say this amount, right? Then the condition is n is greater than p cubed. So now in real world settings, you are working with a data set, and of course it does not follow this condition, right? So now what to do? So what that would mean is that you would require to subsample a little bit more to get this required condition. So what we are doing is we are subsampling a little bit more than fast subsampling would do, which would help us get the required error bound and also makes it run fast. So here is the main theorem of the algorithm for Uluru. So beta is the true parameter which generated the data, and beta hat Uluru is the estimate from Uluru. And it's this complex expression. However, after some algebra, you can see that it boils down to this error bound that we would want, right? So in other words, the error of Uluru is independent of the amount of subsampling, as long as the subsampling is about some threshold, right? Note that the fast subsampling algorithm did not have that. In the fast subsampling algorithm, this term R, like how much we've subsampled, would appear in the denominator. That's a nice property about this algorithm, Uluru. Yeah?
Sorry, so I'm a little confused. Before you were showing us a fast subsampling, the speed was on the order of p, in sub p
Yeah.
squared. And you're claiming that this is on order NP, but don't you have to compute the fast subsampling algorithm in order to do this?
Yeah. So fast subsampling is really fast. So
Okay.
so this thing is like, let's say 1,000 observations.
Yeah.
So on 1,000 observations, it's fast to do.
Okay.
So yeah. So like fast subsampling is really fast, but its error bound is bad. Simple OLS is slower for large data sets, but it's the required error bound.
So to clarify, the
Yeah.
the speed of Uluru is NP plus n subs p squared, but n
Yeah,
sub
yeah.
p squared
It's like absorbed in that. It's absorbed in like the dominating term is NP,
Yeah.
right? And as I said, like any algorithm which looks at all the data, right? It would take and if you have n rows and p column, it has to take at least order of NP. It cannot be faster than that, right? N subs p squared is faster than NP, but as you saw, it's throwing away data without even looking at it, right? Yeah.
Are you assuming the model's correct? That is, there's an error independent of X, or is this just about the algorithm?
It's more about the algorithm. So I'm assuming a simple linear model with additive term, and that's the model
this
that
is
generates.
just you get this for estimating the least squares projection.
Yeah, exactly.
Sorry.
Yeah.
Just to clarify, so because of the first step, I mean, you get the whole thing rather fast in
Yeah.
the end. So all the properties you're showing us of the final estimator, they don't rely on having a lot of observations in this first step, right? That's kind of crucial. Like the first,
Yeah.
like
So-
you say now 1,000, but it's like really not a big number given that the entire size of the data set.
Absolutely. Yeah. So the error bound that I showed is you showed to you is for this. And I mean, in our experiments, so what we do is I just fix n subs as order of NP. But as I said, if you're encountered with a real data set which does not follow this n much greater than p cubed, right? So then you could still run this algorithm. What it would mean is that you would have to subsample more than order of NP or n over p. So in terms of the empirical performance, it gives superior performance over a variety of subsampling algorithm, or fast subsampling algorithms, as well as some of the other algorithms that you would compare it against. For example, the stochastic gradient descent and stochastic dual coordinate descent. So what these algorithms do is they're gradient descent based algorithm, but they compute the gradient only based on some number of observations. They don't use all the data to compute the gradient at each point. And people have proved convergence guarantees of these algorithms. So now, I mean, I showed you the case of n much greater than p, but another case which is very important for, say, folks working with language data, which is very high dimensional, or say brain imaging data where the features are the voxels of the brain. We encounter a setting in which p is much greater than n, right? Let's say you have n is number of patients, you have 50 patients, but you have the voxels in their brain as covariates, so you have 50 million observations, right? So what to do in that case? Like, how can we borrow these ideas to use there, right? So the state-of-the-art algorithm, the fastest thing that you could do is, like, of course, you have to estimate a ridge regression, right, which is a L2 penalized linear regression. So you can work in the dual space for a ridge regression, and this is the error bound that you would get, right, n squared p, right? So over here, what the algorithm that we propose is that you can just do the Walsh-Hadamard transform, which spreads the signal uniformly across all the observations, and then subsample uniformly at random, like an n subs number of observations. So what it does is it shaves off. So instead of n squared, it makes an n log n. So it shaves off a factor of n over log n.
Just to be
yeah.
Sample covariates, not
Yeah. In the p greater than n, right, you would need to subsample the covariates. So just to get the right intuition, like a good comparison for this algorithm would be like something like a PCA. Like, if you have to compute how its accuracy is and how things are, like for such kind of a problem, you would want to do a PCA, right? So what I'm showing is, like, if you were to do something which is a little bit faster than PCA, because PCAs rely on QR decompositions, or like which is like many of the SVD routines also employ a QR decomposition, right? So it might be a little bit slow. So you could uh, precondition it with this matrix, subsample, and then subsample uniformly at random. So note that in this case, we cannot subsample uniformly at random to begin with, because by definition, all the features or the covariates are typically not orthogonal to each other, right? So there would be some of them which would have more signal and the others which would have lesser signal. So we would want to spread the signal uniformly before subsampling. So now, so next, I would like to move forward to some of the work on canonical correlation analysis, which is another, I would say, one of the oldest algorithms. So in canonical correlation analysis, like you are given a set of two matrices. Both of them have the same number of observations, but they could potentially have different number of features, right? Let's say they have Z features and they have W features. So what CCA does is it tries to find a pair of linear transformations, the eigenvectors, call them phi Z and phi W, such that if you were to project Z onto phi Z and W onto phi W, like these, like projected onto their own subspaces, that the resulting, that we would maximize the correlation between those two subspaces. And to be more precise, this is the objective that CCA is optimizing. So it's maximizing the cross covariance matrix, and then it's normalizing by the autocovariance of both the matrices. So note that CCA has very, very close relation to several of the algorithms that we are familiar with. So for example, PCA. If instead of two matrices, we only had one matrix, we just had Z, we did not have W, then it would be Z transpose Z, and this is like the variance maximization formulation of PCA, right, that you could write. Similarly, if W matrix only had one column, that it was n by 1, then it can be shown that this is the optimization of this would give you the least squares solution for ordinary least squares, right? And typically, if you were to like, let's say, use MATLAB or R, and you have to do a CCA between these two matrices, so what you do is you compute the SVD of this thing. It's the cross correlation matrix, and these are called the whitening terms, which convert the non-diagonal covariance matrix into a diagonal covariance matrix, right? So, and of course, the CCA objective, what I showed here, is for two matrices, but you can generalize it to n dimensions, right, for n possible views. And it's possible, and it's a natural fit for lots of data settings where there are more than one views of the data, right? So for example, what computer scientists are interested in is, like, you want to classify this classification task, whether the page is spam or not. And you are given information about the text on the page and the hyperlink structure on the page, right? Or you want to predict gender of the speaker, and the different views are the video and the sound. Or there could be another prediction task where you want to predict what the current word is, and the different views are the words that occur to the left and the words that occur to the right of that word, right? So there was this, yeah.
Do you have an example of a prediction task where this would not be suitable? So when you say views here, so how is this different than just say, just a feature?
Yeah, so that's a good point. So so what does a view mean, right? So I would make that precise in a bit, yeah. So now, yeah. So Kakaday and Foster in the seminal paper, they provided sufficient conditions for CCA to provide dimensionality reduction without losing predictive power, right? And the two conditions that they considered were redundance and conditional independence. So to answer your question, let's say you are encountered with this problem, right? So what would be the most natural thing to do, right? I would just run a simple regression or classification where this would be my Y, and I would just concatenate X and Z and run it, right? That would be the most natural thing to do, right? So let's say if X is very, very high dimensional, say it has 10,000, it's like text, it's very, very high dimensional, it lives in a 10,000 dimensional space, so does Z, it lives in a, so in a way, you are estimating 20,000 parameters if you were to just concatenate X and Z and regress it on Y, right? So what Kakaday and Foster said that what instead you could do is you could use CCA between X and Z to estimate this low dimensional space, which would typically be 100 or 200 dimensional, and then use those projections and regress them on Y, right? And doing that, like you won't lose any predictive power. So now you would say, why would you do that? Like if you won't lose any predictive power, why not just use these X and Z? So the reason you would want to do is that by projecting them into low dimensional space and doing regression over there, you are estimating far fewer parameters. So earlier you were estimating 20,000 parameters, now you're estimating only 100. So what that means is, since you have fewer parameters to estimate, you need lesser data to get to a certain error bound. Or in other words, you get better sample complexity, right? And they said that if you do that, you don't even lose predictive power, because other concern is that, of course, you have better sample complexity, but you have poor predictive power, right? So now the two conditions were that what are the conditions for the two things to be the views, right? Like what do I mean by view, right? So the first of which is redundance. So each one of them, a linear estimator based on each one of them should roughly be as good as based on both of them. It means they cannot be totally orthogonal. There has to be some overlap between uh, there has to be some overlapping signal between the two views, right? And secondly, there's a conditional independence, which is a pretty light condition, which says that X and Z should be conditionally independent, but conditioned on some hidden variable Z. So you can see Z is like a latent variable. It's pretty generic, so it could be, that's not hard to assume. And if you have that, like you can do CCA and we get dimensionality reduction without any predictive power. So now what I'm going to show is like how to use CCA to learn word embeddings. So word embeddings of late have become very, very popular in natural language processing and bunch of other allied fields, right? So what a word embedding is, typically you characterize each word by a low dimensional vector, say 50 dimensional vector, which would capture all the syntactic and semantic information about that word, right? So basically, it's just a set of covariates that go around with a word. And if you're doing any task like sentiment analysis, you're predicting the gender or anything, you can just shove those covariates in there and hope to get a performance bump, say about 1 or 2 points.
So ideally, it captures all the syntax information, but in practice, maybe not necessarily.
Absolutely, absolutely. So in reality, yeah, I mean, ideally it should capture the semantic and syntactic information about that word, yeah. But in reality, of course, it's an approximation, yeah. So, and as I mentioned, like it's a very popular topic of research in and natural language processing these days, and many of you would have heard things like word2vec and glove and several other attempts by Google and Facebook research teams to compute these word embeddings, right? Basically, given a set of words, how would what I want is say some low dimensional, typically 20 or 50 dimensional vector for that word, right? So here is what like a 5-dimensional embedding for some word would look like, right? So, and different words would have these different vectors. So now you can see that you can plot them in 2D and see how they look like are all the adjectives together or all the verbs together, or you can just use them as extra covariates in your sentiment classifier and hope to get a performance boost, rather than just using the word itself, which lives in a very, very high dimensional space, and you might not be able to get good estimates. So as a first pass, you just do a CCA between a word and its context, right? So note that like the CCA objective that I showed, like another way to think of CCA is just a linear regression, right? CCA is a linear regression where you are predicting W using Z, but W has multiple columns, right? So think of it as predicting each of the columns independently and then doing some fixing later on, right? So till now what I've shown is CCA based word embeddings, and they're statistically efficient. I mean, the guarantees were already provided by Kakaday and Foster, like, right? And you could use, and as far as doing SVD on large data sets, there's been like some work, very impactful work done by Halko, Martinson, and Trop in this paper called Finding Structure with Randomness, where they say like how you just multiply a giant matrix with a random matrix and do a few iterations and which involve a QR, a decomposition, and you're good to go, right? So now, just to crystallize things, like what do I mean by doing a CCA between a word and its neighboring words? Like, let's take an example. So let's take a sentence. These are not the droids you're looking for. So you have a CCA between the word and its context. So Z is the words to the left and the words to the right, right? So now, like, how do we encode these matrices? How are these, like, what really is a W matrix, right? So you have to fix some vocabulary size, right? So for this sentence, let's say our vocabulary universe is just 3 words, right? And R for the are part of our vocabulary, and any other word we would just code it as out of vocabulary, OOV, right? So now you can see these are not the droids you're looking for. These is not in one of these 3 words, so it's out of vocabulary. R is there, so there's a 1 here. Not is not, so there's a 1 in out of vocabulary, and the is there, and so on. And similarly for the words to the left and the words to the right, right? So for the word R, the word to the left is out of vocabulary because it's these, right? And for word not, the word to the left is R, right? And similarly for the words to the right. You just concatenate L and R and you do a CCA between Z and W, and you would get the left eigenvectors. Basically what it would do is it would give you V times some low dimensional space, say 50 dimensional vector, and you can just pluck out the word embeddings for the word that you like, and see how they look like. So as I will show later, so these embeddings work well on a variety of natural language processing tasks, right? However, they don't generate efficient embeddings for rare words, right? And as all of us know, like in language, all the words are rare. There are like a handful of words, like the function words and determiners and prepositions, which occur all the time, but like all real words are rare. And in fact, they have a very, very long tail Zipfian distribution, right? So now, in the previous simple algorithm that I showed, CCA between Z and W, so what we've done is, typically for English, the vocabulary, like this vocabulary that you would use, is typically like, say, an Oxford dictionary or a Cambridge dictionary, it would be like 300,000 words, like 300,000 words that occur in English. So the dimensionality of this thing is about 600,000. So you're estimating 600,000 parameters. And so as you can see, since in language, most of the words are rare, like you have to, like for some of these rare words, you have to estimate 600,000 parameters from only a few samples. So you run into sample complexity issues. So just to give you an example, so words like ziti, lasagna, or backpack, if you take like an year's worth of Wall Street Journal or New York Times, they only occur a handful of times, say about 10 or 12. So what we do is, I want to propose a statistically efficient algorithm which has better sample complexity for rare words. And the idea is really simple, that you do a CCA between the words to the left and words to the right, estimate a low dimensional space, and then you do a second CCA between the word and this low dimensional projection. So this two-step procedure called two-step CCA gives better sample complexity for rare words. So I will give some intuition why that's the case. But at least you can see how this is different than what I did earlier. So what I did earlier, I just did a CCA between W and L and R, right? So now what I've done different here is I've done a first CCA between L and R, got a low dimensional space, and then do a second CCA between this and the word itself. So long story short, the main intuition is that predicting a word as a function, as a combination of its neighboring words, especially when those neighboring words live in a very high dimensional space, is a very sparse problem, compared to using the neighboring words, projecting them down to some low dimensional space, and then using that low dimensional space to predict the word, right? So now, like another question arises that, however, in the first step, when I have to do L and R, I'm still working in a very high dimensional 300,000 words dimensional space, right? So won't I face any sample complexity issues there, right? So it turns out that another property of language is that like words are distributionally similar. So the words might be rare, but like they are similar to the words which are distributionally similar and more frequently occurring to them, right? So for example, word umbrage versus annoyance, they are distributionally similar. You could just replace them in text wherever one or the other one appears, right? However, one of them is rare and other one is more frequent. The same is true about unmeritorious versus undeserving. So basically, what this two-step CCA is seen to be doing is it's borrowing statistical strength for rare words from the more frequent words, right? And of course, I have a theorem about this that in order to recover the true state from two-step CCA, you need far fewer parameters, and you can do it more efficiently using two-step CCA. So next, I'm gonna show, like, of course, I've learned these embeddings, but are they any good? Like, I want to show a bake-off against like state-of-the-art methods on a bunch of different tasks, like some of which might be interesting to you guys. And I compare against a bunch of methods like the Brown clustering and some of these deep learning methods and this latest method by Google, which got lots of PR. And I will show it on a suite of NLP tasks, like the performance on a suite of NLP tasks. So first of all, I would just show the nearest neighbor visualizations, like do they make sense to our eyes, what we are getting. And then I will show that if you were to use these as covariates in some task like named entity recognition or word sense disambiguation or Google analogies, how do they perform? And there are several engineering things that you can add on top of this. So for example, you could try different context sizes. You can use exponential smooths and other like theory-inspired engineering modifications that you can do. Sorry. So, so over here, what I've done is I've chosen a center word, and I've seen the words that are nearest the nearest neighbor in this eigenword space, as well as a competitor PCA space, right? So as you can see, like the words that the nearest words to market in eigenword space, like they make much more sense semantically and syntactically. For example, say rupee, you get other currencies, whereas for PCA, you get like some index names and so on. And for which is an Nomura, which is an investment bank, you get pretty much similar, capturing the exact syntax and semantics of the word. Whereas over here, you get brand names in general.
What is it? This is trained on like PTD or?
I'm sorry?
What is it trained on? Or what's your?
Oh yeah. So all the great question. So all these algorithms that I would just mention, all of them were trained on 10 years worth of New York Times. So New York Times released their corpus where they had released all the text from their articles from 96 to 2006. So it's about a billions. I would say a few billion tokens of text, and I just trained like all the algorithms on them. And so it's like a fair comparison in that respect.
In the vocab, you said it was 300,000.
So I use 300,000, but you could, you could do 500,000 and so on, because new words are being added and so on, or like some of the words which they use could be special symbols or something. So yeah.
And so one other thing while we're on this, so then how long did it take with like a vocabulary of 300,000 and all of New York Times?
So yeah, so the eigenwords, like it just requires the SVD, and as I said, like SVD, you could do computed pretty fast using some of the like the Halko, Martinson, and Trop paper that I mentioned. So it took like a few hours, I would say 7-8 hours to compute. Yeah. So now over here, what I want to do is I want to I came up with semantic categories, like some predefined semantic categories, and see how the embeddings look in these categories. So the first category is ears versus numbers, numerals versus numbers, right? So as you can see, like a PCA, it's kind of squishing everything together. However, like the eigenwords embeddings are capturing a nice separation between things which should be similar, like the numerals, years, and numbers. And the same is true about weekdays versus verbs versus pronouns, and nouns versus adjectives versus units, right? Whereas over here, like almost everything is kind of squished together. So this is all qualitative evidence. I mean, it still might be the case that these embeddings are no good, right? I mean, they just, the signal that they're adding on top of what we already get from state of the art is not worth its while. So now let's see some results on task where we use them as extra covariates to uh, to increase the covariates that we already have. So named entity recognition is one of the problems which has gained lots of interest. And the task here is you are given running text like this: UN official EQS heads for Baghdad, and you have to identify the named entity of the entities involved, namely person, organization, locations, or not an entity. So for example, the correct classifier over here would say UN is an organization, EQS is a person, and Baghdad is a location. So, so as I mentioned, the good use of these embeddings is that you have like I would say a system, NLP system of your own, like a classifier that you've trained, that you just append these embeddings to the end of the covariates that you already have, and you want to see the performance boosts, right? So what I've done is all these algorithms are exactly the same, except the only difference is whether the 100-dimensional embeddings that I used were the eigenwords, or were they Senna, or were they word2vec, and so on, right? So these are the F scores and that I report, which is a harmonic mean of precision and recall, right? So as you can see, you get like about a 1% F score improvement on these things. So now you might be saying, you know, how much is one F score, and is it really worth our while? So in these tasks, like named entity recognition systems, they're like highly saturated systems, and even getting a 0.2 F score improvement is like going a big way in this literature, because the systems are already, people have tried pretty much everything that you can think of, like every covariate that you can think of. So like one score improvement is like a big significant boost. And of course, I did some significance tests using like bootstrapped samples, and like these results are significant. So then there is the problem of word sense disambiguation. You're given a text like this: the Bank of Scotland. So does it mean like bank as in river bank, or bank as in the financial organization, the financial institution bank? And this is like cross-lingual word sense disambiguation. So even over here, the accuracy that we get on classifying the test set is eigenwords perform better than like the state-of-the-art algorithms. So now there's this interesting task which was introduced by Google. It's called the Google analogies. So the task here is that I give you 3 words: Athens, Greece. Sorry, 4 words: Athens, Greece. Athens is to Greece as Canberra is to Australia, right? So the relation that you can see, the semantic relation is a capital of, right? So now, and similarly for syntax, you can do write, writes, eat, eats. So the task is, you would be given only the first 3 words. You would be given Athens, Greece, and Canberra, and you have to find the 4th word, that is Australia, right? So, and the way this thing works is that you would compute this vector offset, that E1 minus E2. You would take the embedding for Athens, subtract Greece from it, then add Canberra to it. It would give you some vector. And then you see amongst your vocabulary which is the closest word to this, right? If it's Australia, it's correct, you get all the points. If it's not, you get 0. So it's a very harsh, very tough problem, because it's like a classification of the size of vocabulary, right? And it was initiated by Google. So over here, it's comparable to Google, like Google's word2vec algorithms, but in some of these relations, it's slightly worse, right? But I would say this task was these Google embeddings, word2vec embeddings, they render themselves nicely to this kind of algebraic operations like a vector offset. So no wonder they perform better. I mean, if we really want to do well on this task, like you could train an embedding based on optimizing this particular loss function, right? If we were to do that. So in conclusion, this talk proposed computationally and efficient algorithms for linear regression and canonical correlation analysis. For linear regression, the runtime is order of NP, and the statistical guarantees are exactly the same as the textbook linear regression. And for canonical correlation analysis, we get better sample complexity for rare words. And as far as computational efficiency is concerned, as I mentioned, I use some engineering tricks on top of Halko, Martinson, and Trop, which is, I would say, like one of the seminal papers in this area, and to help things run in order of n squared times, where n is the number of observations. And you can use this improved CCA to generate word embeddings, which could be used in pretty much every NLP task that you can think of, from named entity recognition to word sense disambiguation to sentiment analysis to analogies and what have you. And I've also used these for generating human brain parcellations from fMRI data. So so in terms of my research portfolio, so this work I did while I was a grad student at Penn with my advisors Lyle and Dean, and most of this work has already been published. So currently I'm a postdoc at MIT working with Professor Sinan Aral, and I'm working on several projects on social network analysis and digital transformation of news media, where I'm doing more causal inference and applied econometrics work. Thanks. Yeah.
I'm still trying to wrap my head around it.
Yeah, sure.
So I guess, so my understanding is that one of the ways that in the linear regression context, one of the ways you get the statistical guarantees is that it's got to, you have some lower bound on the growth rate of the fast subsample that you're using the first step, right? It's got to grow at a certain rate in order for that to work. Is that?
Yeah. So yes. Yeah, so its rate is this, right? N sub p squared.
Go forward to the picture with the mountain.
Yeah. Okay.
Right. So, am I wrong that as n grows, you're also growing the size of the subsample?
Yeah.
So I get so
it grows linearly in
Yeah. So I guess my question is like what, but so I guess how much of the benefit are you getting on the error bound just by increasing the subsample size as n increases, rather than this kind of additional step of doing this kind of plug-in estimator that you use on the second side? Like, what if I, how much better is an error bound if I just take allow n sub to grow?
Allow what to grow?
So when you do this analysis,
Yeah,
I guess
yeah.
when you're going back to this slide before, when you're doing the analysis of doing the kind of analyzing the efficiency and the error bound of
Yeah.
the fast subsampling, you're choosing a fixed. You're choosing like a fixed n sub.
Absolutely.
Right here, you're kind of putting some. Here, you're allowing n sub to grow.
Yeah.
And then you're analyzing the effect on your algorithm. But what if we just reanalyze, they kind of do the same kind of thing going through, analyzing the fixed subsample method, but allowing the subsample to grow within.
Yeah. So that's a good point. So I mean, as far as theoretical guarantees or fast subsample are concerned, I mean, like its runtime stays the same, and its error bound would. I mean, I see what you're saying. What you are saying is. That this n subs would increase, so this error bound would also improve, right?
Yeah, I guess it's just like in the limit, these things are going to get. Basically, I guess in the limit, what you're doing is you're just kind of like mixing the two together. You're kind of, there's a little bit of a trade-off, but you could. I guess I don't necessarily. Like, I don't know. Why don't I just grow the size of the subsample, and then accept whatever kind of minimal the loss in the error bound that they get.
Yeah, I mean, you could do that, but in a way, like that's what Luru is also doing. It's saying that if the subsample is about some threshold, right, that the error bound becomes independent of the amount of subsampling, and
yes. So if, for example, if you can, if you have tests and you can tell like for the subsample in terms of the n and the p, and then your subsample n, what will be usually the optimization that till that threshold wouldn't really improve.
Yeah, so I see what you're saying. I mean, in fact, like in the paper, I do some like in the simulations results that we show in the fast subsampling, we do vary it from very, very small number to a higher number. I mean, as you're saying, and it turns out like the error becomes pretty close to what Uluru does. But like Uluru, like it gives you like how to find that I would say threshold up to how much subsampling you should do in a more like it gives you a bound for that. So I mean, I can like we can talk more about it offline, but I mean, I think that's a great point. That if like in a counterfactual world where this thing doesn't exist, that's what I would have also done. Like increase the amount of subsampling, and try around like do a binary search or something and see how things go. So yeah. And also regarding these word embeddings, I must mention, so like I have software, like in fact I've already trained these word embeddings on say 10 years worth of New York Times of text. So if so I'll send a link to Pamela, which she can share with everyone. So there is software also if you want to train your own on some new data set, like some congressional speeches or something. Or I've already trained them on New York Times and for a bunch of different languages like English, German, Dutch, Chinese, and Japanese, I guess. So you could just use the pre-trained vectors, or you could train your own based on your domain that you're working on.
Can I ask a
Yeah.
question? You mentioned the neural image
Yeah.
work. Can you tell a little bit what you are doing with that and or how this applies to that work?
Yeah. So in neuroimaging, like the problem is, it's the p much greater than n setting. You have lots of features which are like the voxels in the brain, and the n is the number of patients, which is say typically 50, right? So in neuroimaging, it's a problem that if you're given a fMRI image, you want to segment that image into some network, like say default mode network, like it's like 5 or 6 regions of the brain. You have to show where they are, right? So typically, what researchers do, like doctors have these predefined atlases. They would say, hey, this is the area where like precuneus is, or prefrontal cortex is, and so on, right? So, however, what they don't allow for is like person-specific variation, right? Like these things could vary from person to person. So what we do is, and moreover, there are things specific to that particular fMRI, some MRI fixed effects, you could say, right? So basically, the algorithms what we propose is that uh, that you take the physician specified regions of interest like precuneus or prefrontal cortex as a prior, and then you let data to explain, like change the boundaries of these ROIs in the brain, so that you also do a good job on prediction. So in this case, what you would want to what physicians really want to predict is, I mean, like you want to like they typically want to do like they want to diagnose Alzheimer's at a very early stage, right? So using these features derived from fMRI images, and if you were to use them to predict whether a person has Alzheimer's or not, that's probably not interesting, right? Because you already have Alzheimer's. So what they would rather want to do is they want to do an intervention at a very early stage and predict like a mild cognitive impairment. So you're looking for a very subtle signal, a change in the hippocampus, or like a little bit change here and there. So you want to come up with an algorithm which will give you like a significant boost in accuracy of predicting whether the patient has mild cognitive impairment. So it turns out like if you were to refine these ROIs in a more data specific way, using some of these matrix decomposition techniques, you get far more signal which would let you predict a mild cognitive impairment compared to what doctors had been doing till now, which was just using they have a predefined region of interest. Here is prefrontal cortex, here is hippocampus, and so on. So I can share the paper with you if you could send me an email. Yeah, thanks. Yeah.
So two questions about the eigenwords. So
Yeah.
how many components do you use in that first decomposition? And then in terms of time, how does it run versus word to vec?
So yeah, so that's a great question. So I mean, like as far as the theory is concerned, you can keep the same k, which would be 50 in the first step also. So what I do in my software and the embeddings that I shared publicly is like I typically do a little bit higher dimensional space here. So I typically use like 100 here, and then finally this is 50. And as far as this speed is concerned, I mean, I have this in Java, and as you know, like Java is like reasonably slower than Word2Vec, which is in C++, right, or C. So as far as speed is concerned, I would say it would be slower than Word2Vec, like in absolute terms. But in some of these some of these tasks, like the better performance on rare words is worth it compared to Word2Vec. I mean, Word2Vec came pretty much around the same time, came in late 2013 or something when we were doing this. So and we did like very thorough comparisons against it, but like its performance on some of these rare words could be is sometimes not that good. But the thing is, like, it runs really fast, you know. That's why you could train it on billions of billions of tokens of text, you know, in like a couple of hours or something. So it's a little bit slower, definitely slower than Word2Vec. But if I were to do like total engineering on this, I think like there is some speed gains to be made based on the implementation. So also, yeah, what was that? I forgot. Yeah. Yeah.
Out of curiosity, did you guys do any subsequent experiments where you extended the context around the words? So instead of just using the left or right word to, I mean, very rapidly run into sparsity issues, but say, like, use a bigram on each side, for
So
example.
yeah. So typically in all these results that I showed, we use 2 words to the left and 2 words to the right.
Okay.
So, and it turns out that in language, 2 words is pretty much enough. Like you don't need, you might think that you might want to consider 20 words to the left and 20 words to the right, right? Irrespective of the sample complexity issues. But turns out for for English at least, just a couple of words to the left and 2 words to the right is suffices, you know, because you just need that much context to disambiguate what the word is. For other languages, those things might be different. You might have to consider wider contexts. And I think, as I mentioned on one of the slides, so another thing you can do is you can use exponential smooths, right? Which is like a recursive way of adding much broader contexts of words to the left and words to the right. Yeah. Yeah, I mean, yeah. So we do, yeah. So we do like the standard pre-processing that's done in these things, and and I think like there is this thing called Porter-Stemmer algorithm, which has which like stems the words and removes some punctuation. So it's nothing special. Although, I mean, I think like uh, uh, one of the strong points of eigenwords is that you don't need to do any of that pre-processing. Like typically what happened in NLP earlier was people would like hand tune the input data in such a way that you would remove all the stop words and all the other rarer words, and then on the clean text you would run those things. So in the very first experiments that I ran in several years ago now, just used just the raw text. You know, I didn't even strip off the HTML tags. You know, they were still there. So, but still, the quality of words that you would get, like they are like really good. So yeah, so you don't need cleaning of like extensive cleaning of text. So yeah, so what I was forgetting earlier was, so there is a strong connection between Word2Vec can be seen as a matrix decomposition technique. So there was a paper, I think a couple of years ago, if you can send me an email, I could point it to you, which showed that Word2Vec is also doing kind of a matrix decomposition. So it's not really deep learning, you know, it's like, I would say if it was a neural network, Word2Vec, it would be like 0 layers, you know, so, which is, so yeah, so they're doing a matrix decomposition and they are maximizing point-wise mutual information. You know, yeah, yeah.
Sorry, so there are two things. So first, I want to check with you whether my intuition is correct on the OLS. So essentially, you can see the betas as the ratio between the covariance between the x's and the y, and the variance of the x's, right? So your methodology is essentially, I pre-compute the variance because it's very costly computationally to invert the matrix. And then I plug that in a standard OLR regression with the rest of the data.
I mean, I think as I mentioned,
Correct?
I mean, you're on the right track, but I think like as I mentioned earlier, yeah. So in this cost, or say this cost, this NP squared is just the cost of this multiplication. So inversion is not a bottleneck here because n is much larger than p. Inversion would take p cubed, right?
Okay.
Inversion is cubic in the size of the, so it's np squared plus p cubed. So this term would dominate. So inversion is less of a concern here. The bottleneck here computationally is the multiplication. Yeah.
Okay. But still it's true that you basically, the trick here is to pre-compute that and plug in later.
Yeah, you can think of it like.
And then my question is, how does it cost this in terms of efficiency of the estimator? So definitely your estimator is not the best linear estimator, but how much is the cost in terms of efficiency? Not computational efficiency, but here statistical.
But I mean, I think like as I showed, like the error bound, you get the required error bound, right? You get the, as far as some other notion of efficiency, I mean, I did not compute other, like there might be some other metric that you're looking at. But as far as the error bound, this notion of consistency, it achieves the same.
Yeah, definitely. So I
Uh-huh.
agree that you have a consistent estimator, but my
It might not be best linear unbiased estimator.
Yeah, definitely is not, because otherwise you're violating those.
Yeah.
Those marked here, but
Yeah, that's a good
maybe
point.
it would
Yeah.
be nice to have maybe some simulation of pictures where you show in terms of efficiency how maybe if the sample is big enough, there are no big costs in doing that. But
Yeah, I mean, I think that's a good point. Yeah, so that's something to look into. Yeah. Yeah.
So issues of numerical accuracy come into this at all?
For this,
Yeah. I
Uh,
mean, converting matrices is.
yeah, it's
stuff,
like, yeah. So yeah, like sometimes they do, but I mean, I think like typically what they do is you add some regularizer. You know, you add some like, I mean, say some slack term to the diagonal of the matrix. You know, if sometimes things are not invertible and so on. So, but other than that, I mean, I think it's like it works fine. Yeah. I mean, in a way, what we are doing is we are just computing OLS on a much smaller sample, and then correcting that estimate, in some way which doesn't blow up the runtime.
Thank you so
Great,
much.
thanks.